Hey guys, it's great to be here. So how do you even learn about partition in Postgres? Why do you even need that? I usually, anytime I speak about Postgres optimization, I like to talk about this thing, uh, that thing, course of August. So that is something that happened to the company I'm working at right now. So it's Hub stuff. We do workforce analytics, time tracking, etc., and we deal with a lot of data, terabytes and terabytes of data. So we've seen all possible issues that could happen to Postgres. And about 5 years ago, we started having what we later called the curse of August. So what was it? That is screenshot from AWS Aurora, which shows you the CPU load on our database. And that dotted line at the bottom of it shows you the physical limit of the CPUs available on the machine. And as you can see, we hit some limits. And every August, we would start having that. So 7 months heading into the August, everything's looking great, everything's perfect, customers happy. August 1st hits, that start happening. And every year, there would be a different story behind that. And every year, things would get only worse and worse. So by the end of August, we feel like we finally won this battle. Everything's perfect. Everything's working. The next August comes. That dotted line is still the limit of CPUs, just FYI. So again, we fight the battle. We feel like we've done it. We won it. We move forward. Next August comes. You can see that the dotted line gets lower and lower and lower on every single screen. I won't show you more screens because you will be terrified. And I mean, I don't believe in magic or coincidences, but it's funny that these things only started happening as soon as our head of DevOps joined us. Only that year. He's there, he's smiling, give him a round of applauses. Yeah. By the way, he joined our Ruby club today. He got his first Ruby passport, so now he's one of us. One of us, one of us. And as always, behind every incident, when you do the postmortem and everything, it's always great to see the story that always happens behind the incident. And I'll show you just a few screenshots that led us to learn what partitioning even is. So when one of that screenshots happened, we had this fun conversation on Slack. Yep, things are 80 times slower than they should be. I'm smoking right now. Can somebody take care of that? Yeah, you always choose the wrong time to poop or smoke. I mean, that's the hard truth of being a remote company. Yeah, but all of that, all of these fun and sometimes not fun midnight stories taught our company a lot about scaling Postgres. And today I want to talk about probably one of the best tools in the Postgres toolbox that you gotta use in certain cases. We'll talk about that. And partitioning, it has this mystery around it that it's overcomplicated. You have a lot of maintenance around it, which changed a lot with the recent versions of Postgres. And we'll talk about that today. In fact, so I have 23 slides, right? That sounds like a lot. Only single slide will show you exactly step-by-step guide how you need to partition your database. The rest is about whether you actually need it, and if you do, how to get prepared. So it's that easy. So what's partitioning? So table partitioning lets you split a large table into smaller tables so that every time a query hits this table, it works on a smaller data set and it can perform better if you do things right. So just let's dig into some theory and then we'll get into practice. So basically, when you partition a table for your application, technically nothing changes. Because let's say you have the activities table. And after you partition that activity table, your application keep working with the activities table. So on the surface, nothing changed for your application. But behind the scenes, you have this parent table, let's still call it activity. And behind it, it plays the role of the facade for smaller tables. And each small table contains this chunk of data that used to be in that larger table. And every table would basically replicate the same schema like your parent table. All the same indexes, all the same foreign keys, but it just contains the small chunk of data that used to be on that table. And there are multiple ways you can partition your table. So there are actually 3 natively supported by Postgres, and there is the 4th one that is supported by one of the tools. So there is a range partition. And actually, if you decide to do partitioning, that is highly likely scenario you're going to follow. So range partitioning basically lets you split your table by certain ranges. Like, for example, only put the data that comes in May of 2025. That what one partition will handle. And usually you do ranges by timestamp. The other type of partitioning is list partitioning. So the picture won't change, just basically the logic behind partitions change. So the list partitioning is, let's say you have a category column in your table, and let's say it says, I don't know, like clients, users, vendors, right? And for whatever reason, you want to have data assigned to this category in different partitions, so pretty statically defined partition list. And the last one is the hash partitioning. So basically it's like, let's say you have 3 partitions and you want to partition by index, so you just apply modular operation and just data uniformly distributed across these 3 partitions. Again, theory is pretty simple. Now, actually, how do you get into partitioning? Because again, there is a lot of mystery behind it. There is a lot of complicated guidelines, but it's not that hard. Like I said, you'll spend more time planning for doing partitioning rather than executing it. So let's start with the first and the most important step is you need to analyze and understand the trade-offs behind partitioning certain table. So first of all, partitioning lets you handle high ingest of data at scale. What does it even mean? Let's say you have a table that just grows every day massively. Like maybe you're working on the IoT thing, or you're collecting a lot of analytics, etc. So basically, the rule of thumb, your data is growing constantly and regularly. And at scale means you have at least 70 gigabyte of data in this particular table. If you go on the internet and like look for suggestions, what Postgres team, for example, recommends as a threshold for deciding whether you want to partition or not, they say it's 100 gigabyte. And yes, definitely when your table is at 100 gigabyte, just one table, not the entire database, you certainly want to look into this table partitioning. But as soon as you reach 70 gigabyte and your data keeps growing, that's the moment you should start considering it. So the second thing, it improves query performance. And important note, if you look a little bit to the right in front of this improves query performance, there is can hurt performance. And yes, it's a trade-off. It depends on multiple factors that we'll look into in the next slide. And the third great pro of having table partitioned is it simplifies data retention. So all of us who have experience working with like time series data, you know that you mostly need only the most recent data in your table. So you want to retire the older data. And usually you would do that through delete queries. As soon as your table grows over 50, 60, 70 gigabytes, it introduces a lot of problems. First of all, these queries are slow. It introduces a lot of database bloat. It introduces a lot of auto-vacuum problems. So a lot of maintenance hell, actually. And the negatives of doing partitioning wrong or doing it prematurely is, well, first of all, it always adds operational complexity. Yes, it's way simpler to do table partitioning these days than it used to be 10 years ago or even 5 years ago, but one way or another, it adds operational complexity, and we'll have a slide dedicated to it. Again, like I said, it can hurt your performance if you partition by the wrong key, which we'll get to in a moment. And last but not least, it doesn't make sense to do that on small or stable tables. Well, small tables, again, make sense, like I said, and unless your table is at least 70 gigabytes of data, you shouldn't even look into it. So if you have a table that is 10, 20 gigabyte and you think maybe I should, there are way better optimization practices that you should do first before doing that. The only reason for partitioning smaller table that I can recommend, and actually our team did that first, is if you're just starting and like, hey, I have these multiple large tables and I want to partition them, can I do it at a smaller scale? then yeah, give it a shot. It will unlikely make things worse for you, but like that's a great thing to test the grounds. And stable table means that yes, it might be a large table, but it doesn't grow in size really quickly. So it grows like, I don't know, like maybe a few gigabytes a year. It's growing really slowly. You have enough of time to do deletion of all data, then it doesn't make sense. You will introduce unneeded operational complexity. All right, so let's say you did the trade-off analysis. You decide, yeah, actually, I have a large table. It's growing fast. I want to move forward. What do I do next? So the next logical step is you need to choose the right partition key. So a few slides ago, we've seen how partition works in theory, but in practice, first you need to understand by which key, by which column will you partition data. So for example, if you have a time series data, then something like created at is a reasonable candidate because again, you want your data to be organized by months, weeks, or years. If you want to split your data by categories, then yeah, you may consider multiple categories. But yeah, first of all, you need to understand what is the right partition key. And in order to do that, you need to do three things. First of all, analyze all the query patterns inside your data, inside your code base that are hidden in this particular table. You want to understand that after you partition a table, every single query going into this table must have a partition key in the where condition. It just must. Otherwise, Postgres just doesn't know which specific partition you want to hit, and it will scan the entire table, and it will be even slower than just scanning unpartitioned table. So that is why you need to understand, do I even have a pattern of queries in my code base that can actually utilize partition key? And as soon as you found it, I bet you'll find cases in your code base where you have open-ended ranges hitting this partition key. For example, if we're talking about data time step ranges, you will definitely have cases like, find me something where created at is less than this. And if you do that on partition table, less than this means Postgres will immediately identify which partition it should scan first, but less than this tells it, oh, and also scan all the partitions that have data less than this, which means it will hit, I don't know, if you have 10 partitions that have data created earlier than March, it will go through all of them, scan each of them separately, merge data together, way slower than doing it on the unpartitioned table. So first of all, understand your query patterns and understand which partition key would be the best match. So you did that. Now, what is the partition size? So like we said, every partition has the ranges. If we're talking about timestamp, let's say you decide to break it by week, by day, by months, by year. Postgres supports all of that. Again, you need to analyze which exactly partition size is the best case for you. For example, maybe your clients mostly do reporting on the weekly basis, and this is where the most complex queries hit this table. Then yeah, weekly partitioning is probably, weekly interval is the best choice for you. Just a few seconds ago, I said it's not really great for performance when Postgres tries to analyze multiple partitions. Yes, if we're talking about dozens of partitions, but if you need to analyze just multiple of them, 1, 2, 3, then it can merge this data pretty rapidly, so it's no big deal. So first of all, again, as always, as on the previous slide, analyze your query patterns and understand how your customers use this particular table to understand, to make sure that the most complex and the most heavy queries will almost always fit within one partition. And ideally, you want to have partitions that fit enough of data, but not too much. Because again, way too much data in the same partition, you basically have the same large tables. Doesn't make sense. When you have a few partitions of a small size, but there are hundreds of them, again, it makes it harder for Postgres. Merge this partition, maintain it. The most modern versions of Postgres, they claim they can easily handle up to 1,000 partitions per table. We haven't tried it. Like our worst table has about 160 partitions. I can tell you it deals with them really easily, no problem, no degradation for performance. But honestly, I don't feel confident going over 200-300 of partitions per table. And define a data retention strategy. So that's actually a reasonable follow-up to what I just said. Postgres doesn't really work great with large number of partitions. So over time, you need to find a way to get rid of older partitions if you can. Otherwise, again, like I said, you don't want the number of partitions to grow infinitely. Okay, so the next thing, let's say you decided you want to do this. You found the partition key, you found the partition range, all is great. Now you can immediately go to your Postgres instance in both staging and production and enable these three settings. They won't change anything for your unpartitioned table, but they are must-have for before you start partitioning your data. Because otherwise, not only you won't see benefits of partitioning, things will get slower even if you do the previous steps right. So let's just quickly go over these three settings. So enable partition-wise joins. Basically, what it tells Postgres to do, if let's say you have two tables, both of them are partitioned, and your query want to join them. If you don't have this flag on, it will just scan through all the partitions. Even if you have where queries defined properly and everything, if you try to join two partition tables and you don't have this flag on, disaster. The next one is enable partition-wide aggregates. Basically, whenever you do aggregates, like count, max, mean, average, whatever, on a table, if you don't have this setup, and again, you have all the where conditions properly defined, Postgres will do aggregates slowly, inefficiently. If you have it on, it knows how to efficiently merge the results, even if it has to touch multiple partitions. And the last one is enable partition pruning. Well, this is like the silly one in the sense that if you don't have it on, Postgres will always scan all partitions, even if you have boundaries defined, which is like, doesn't make any sense, but hey, Postgres team decided that we need some fun in production and they just disabled it by default. So FYI, like if you decided you want to go with partitioning, go enable it, doesn't change anything, you don't have to restart your database, nothing, just absolutely safe. All right, so now we have all the theory in place. Your team experimented with, not experimented yet, but your team decided the boundaries, decided how to move forward. Now, before you do anything in production, obviously you need to experiment and iterate. Even if on paper everything sounds great, you want to make sure you have the proof of that. So first of all, you want to test partitioning on the clone of your production database, not some data sets that you have, not some clean data that you use in staging or anywhere. Just clone your production database and do throughout all the partitioning steps, because then you want to run, explain, analyze, and emulate some production-like traffic to make sure that the way you partition table actually gives you the results. So you need to measure your performance before doing the partitioning and right after. And you want to make sure that Postgres Planner is taking into account everything and you are seeing significant improvements. And by significant, we're not talking 5, 10% of improvement. Like partitioning isn't worth it for such a marginal improvement. We're talking 2, 3, 5, 10, 50 times faster. That's how fast it should help your queries to become. And let's say, again, you tested everything on production clone, everything's working, you're happy. Then if you have some sort of a shadow environment or a staging environment, do partitioning there and let it sit there for 1 or 2 weeks while your development team is interacting with it, because you might spot some things that you just missed. Things happen, just let it sit in the shadow environment for a little bit. Like our rule of thumb, actually, I said here 1 to 2 weeks. Our team was even more skeptical, so we let it run for 2 to 4 weeks. But I would say 2 weeks is a sweet middle ground. And before you get into partitioning itself, the last but important step is to choose the right tool for your team. And at the moment, there are 2 great choices on the market, pgslice and pgpartman. Spoiler alert, our team decided to go with pgslice despite you seeing more red crosses here. I'll explain in a moment. So they're distributed differently. So pgslice is just a CLI or a Ruby gem. You just download it, you just use it. pgpartman is Postgres extension. pgslice only supports range partitioning. pgpartman, as you can see, supports everything. And it also supports the type of partitioning that I didn't explain a few slides ago, which is multi-level partitioning. So that's like a 2-dimensional array. Not only you partition table, let's say by the list, by the range, but you want every range to also be partitioned by the list. you can have such a complex data and you don't feel comfortable going with the database sharding, so you may want to experiment on a single instance, then it's just some meta level partitioning. We've never done it. I can't recommend it. Maybe it's great, maybe it's not, but it's there just in case you need it. And the ease of setup, pgslice just wins this battle badly. And this is honestly one of the reasons we decided to go with it. Like pgpartment gives you like incredible set of tools you can use. And it being part of Postgres lets you to later do Postgres maintenance a little bit easier. But because our team was already familiar with Kubernetes and familiar with Ruby really well, obviously, we're a Ruby shop, pgslice just fit our team really well. We needed only rage partitioning, so we decided to go with it. But again, every team has their unique needs. And the most important slide of the presentation, the how many? 6 steps that you actually need to do after you did all the analysis to perform database partitioning. So first, you always create a separate partitioned replica table. So let's say we are working with visits table. We want to partition it by creating that column, and we want partition size to be 1 month. You call pgslice prep visits created at months, and it just clones the schema of your original visits table, and it makes it partitioned. Operation is incredibly fast, 0 downtime, nothing your database won't even notice. Step number 2, you create partitions. Again, depending on how you want to handle your data, you may want only partitions in the future, or if you want to retain existing data, you want partitions in the past as well. You decide how much data you want to keep in the past. You run pgslice, add partitions, and it adds like these sub-tables to just newly created table. 0 downtime, 0 impact on your database, nothing will happen. But then you can see 2 steps that they have like this clock icon by them. So this is where you'll spend a lot of time, depending on the amount of data you have. So pgslice fill basically starts copying data from your original table to your partition table. If you have gigabytes and gigabytes of data, that will take days. So be aware. But it has the sleep command, it has next command in case you need to pause it, in case you want to ensure your database isn't throttled. So that is very helpful. Again, it can take somewhere between a few hours if you have just a few tens of gigabytes of data. It can take up to multiple days if you have way more. And then step number 4, before you start using a new table, you need to tell Postgres to analyze this data. I mean, you can do that with just regular Postgres analyze command. I mean, pgslice has it all for you, but basically it's just regular Postgres analyze on top of your new table so that query planner in Postgres knows the structure and knows how to handle this data going forward. And then pgslice swap basically copies, so it changes the names of these tables. So the original visits table becomes visits retired, and the visits intermediate table becomes visit. It happens inside the same transaction. So if you want to do online migration, I would highly encourage you to do that during the low traffic hours. Usually happens really fast. We didn't notice any issues, but hey, every team is special. And then step number 6, really fast, basically pgslice fill visits swapped. Tell the tool to, hey, while we were doing swap, there were new data inserted in the old table, so just fill the rest of the data that wasn't there. That's it. You can do this sequence while your application is running online, perfectly fine. You can go to maintenance, perfectly fine. We did both worked really well. But yeah, that's like literally after you decided on your partitioning strategy, these are just 6 steps that you need to perform. Maintenance overhead, like that's our final part. There will be maintenance overhead, 100%. So the 3 important things to keep in mind. Now, going forward, if you want to add unique indexes on a partition table, they must always have partition key on it. Otherwise, Postgres won't even create it. Like nothing will fail. Nothing will fail in production. Even if you try to do that in production, Postgres will just give you an error. Hey, partition key is missing on a partition table, just FYI, so keep that in mind. Secondly, you need to detach old partitions regularly so that your data set size just doesn't grow infinitely. And like I said multiple times, Postgres just doesn't work with well with really huge number of partitions. And last, which is like actually like a facepalm one, because I just don't get it. Forget about simply adding indexes concurrently. that's gone. You won't be able to do that with the partition table. It just doesn't work. So if you try to add index concurrently on partition table, what's going to happen is Postgres will add the index immediately to your parent table, super fast, and then table by table by table, partition by partition, it will go and add index one by one by one, which will introduce locks, and your application just goes down. We tried, nobody liked it, highly do not recommend. This is the solution to this problem. Like at the bottom of it, you can see the source, the blog post that shared like the idea how you should do that. But basically, long story short, I mean, if you decide to follow it, just convert this into some migration helpers so that your team doesn't have to write this code all the time. Long story behind that is you add a meta index to your parent table, and then you go iterate, like you tell your Ruby script to iterate sub-partition by sub-partition, add index concurrently to it, and that's it. And Postgres will just edit nicely and everything will work beautifully. That is it. Thank you. I hope you're not afraid of Postgres partitioning anymore. It's quite a journey, but if you are past all possible query tuning on your table, and like I said, it keeps growing, that's your way to solve this problem once and forever. Every table we've ever partitioned keeps working like magic. We just forgot about all possible problems, and we forgot about post-partitioning. So the index one, like that was a surprise to us. Other than this, yes, keep partition number reasonable. So remove the older one. And like these partitioning settings, like we discovered them only after. So, but now you know, you don't have to enjoy that. Yeah, but other than this, it's really that easy. Like if you follow that particular algorithm, that's actually the algorithm our team follows every time we want to partition a new table now. So that is like literally a hands-on battle-tested algorithm that just works perfectly. Go ahead.
Was there a reason that your database performance tanked every August?
It's just seasonal. It's just the reason it did tank. So because of the type of work our customers do, they would usually have a slowdown in their business in around the vacation time. Postgres will change its query plans to work with the new, smaller, lower frequency data. Then customers are back in August, and Postgres is like, WTF, I wasn't ready for that. So that was the reason.
Awesome.